Welcome to another lesson on trig identities. In this lesson, we'll be looking specifically at the sum and difference identities. And so we'll talk about what those identities actually are, so we know what they look like. And then we'll look at how we can use them to simplify expressions and to compute exact values. And then at the very end, we'll look at how we can use these identities to prove additional identities. Now, before we really get into what the identities look like, there's sort of an example I want us just to consider. And it's kind of a mistake that would seem like an obvious thing to do, but in actuality, it turns out that it doesn't work. And unfortunately, because it seems like an obvious thing to do, a lot of people try to do it and it doesn't work. So the question we want to think about is it possible to distribute a sign across an addition, kind of like you would multiplication. So in other words, if you had the sign of a plus b, so a and b are just two numbers, is it possible to rewrite sign of a plus b as the sign of a plus the sign of b? So can you kind of split it apart and distribute the sign? And so to do that, I just want to look at a simple example here. We want to look at the sine of 30 degrees plus the sine of 60 degrees. Now, we know that the sine of 30 degrees plus 60 degrees is really just the sine of 90 degrees. So this isn't what I'm actually talking about. We just want to compute what the actual value is so we have something to compare to when we do the mistake. And using our unit circle, we know that the sine of 90 degrees is 1. And that's because, again, on the unit circle, 90 degrees is the point up at the top, which is the point 0, 1, and we're taking the y coordinate, which is 1. So we know that the sine of 30 degrees plus 60 degrees has to be 1. So if we tried this little step of splitting the addition apart and distributing the signs, do we end up with a 1 as well? So to sort of illustrate the mistake that people are going to make is if we had the sine of 30 degrees plus 60 degrees. So we're taking the sine of the sum of those two angles. Okay, the sort of common mistake, and it is sort of an obvious thing to try, but it just unfortunately doesn't work, is we want to compute what's the sine of 30 degrees plus the sine of 60 degrees. Okay, now using the unit circle, we know that the sine of 30 degrees is a half, and we know that the sine of 60 degrees is a square root of 3 over 2. Now, this doesn't turn out to look like 1. Okay, we have some fractions in here, but just, maybe something crazy happens and that turns out to be 1. So let's compute this as a decimal. Unfortunately, when we do that using our calculator, we're going to get something around 1.366. which obviously is not 1. Okay, so again, we know that the sine of 30 plus 60 degrees, which is really just the sine of 90 degrees, we know that has to equal 1. Okay, so again, the question is, can we take this sine of 30 degrees plus 60 degrees and split it apart and compute the sine of 30 and then the sine of 60 and combine them together? And again, the answer is that no, we can't do that. Okay, so again, this is a really simple example because 30 and 60 degrees are really nice and easy to work with, but what if they're not nice, easy to work with values? Okay, what if they're not the unit circle numbers that we're familiar with? Or what if they're just some expression dealing with x or theta or something, and we can't, we're not actually going to solve for it or something, we're just trying to simplify it. So again, the result here is that we can't split it apart. So we need some way of simplifying the addition or the sum or the difference of the sine or cosine or tangent of multiple or two angles. Okay, so let's actually look at what the identities are. And we're going to look at 3 sets. Again, remember, sum is just an addition, difference is a subtraction. So if we have two angles, or really just two numbers, a and b, and we're trying to compute the sine of their sum, so sine of a plus b, or their difference, the sine of a minus b. Okay, so we have these formulas that we'll look at here in a second, and we're also going to have another sum and difference pair for cosine and again for tangent, and each one's a little different. So for sine, notice in the ordering, in both cases it's sort of alphabetical. You have the A and then the B, and both of these A's and then B's. And then when you look at the A's and B's throughout the rest of it, it just pretty much alternates. So A, B, A, B, A, B, right? Same thing with the difference, A, B, A, B, A, B. With sine, we go, if you kind of follow it across, notice both of them go sine, cosine, plus or minus a cosine sine. So again, it's sine, cosine, cosine, sine. And then notice that whether it's an addition or a subtraction here matches whether it was originally an addition or subtraction over here. Okay. Now, just one comment at this point. Going forward, including the sum and difference identities here, all of the future identities we talk about are going to be on your identity sheet. So you don't have to actually have them like 100% memorized. You can use the identity sheet on your homework and tests and stuff like that. But you still have to be familiar enough with the identities that when they appear in a problem, you recognize them. Okay, so you should be familiar with, the sign of a plus or minus b and how that can be re-expressed as sine, cosine, cosine, sine. Right? And it's going to be a little different when we get to the next group of properties. So again, you don't have to have these perfectly memorized, but you should be very familiar with them once you see them. All right, so let's kind of compare that with cosine. Again, for cosine, it's still AB, AB, AB. Whether it's plus or minus, it's still AB, 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 right? So some things that change between the sines and the cosines. Remember, sine went sine, cosine, cosine, sine, so it flipped the order. When you're dealing with the cosine sum and difference properties, it's cosine, cosine, and then sine, sine. So when you have two cosines together, plus or minus two sines together, then you're potentially looking at the sum and difference. And then the other thing here is whether it's plus or minus on the right side is the opposite of whether it's plus or minus over here. So if you have a plus b, you're going to have a minus here. And if you have a minus b, it's going to be a plus here. Okay. All right, and then the third group is tangent, which kind of looks a little different. Remember, tangents sine over cosine, so it kind of uses some different properties here. But if you had the tangent of a plus b, that can be rewritten as the tangent of a plus the tangent of b. So it's almost like you could distribute that, but it's part of a fraction, and you have to divide by this 1 minus tangent of a and tangent of b. Okay. Now notice that these two fractions are pretty much the same. It's still AB on the top, and it's still AB on the bottom. In both cases, AB, AB. So that alphabetical alternating AB, AB still works. If it's tangent of A plus B, then the numerator of your fraction is a plus, and the denominator is a minus. If it's tangent of A minus B, then the top is the same, it's a minus. The bottom is the opposite, it's a plus. Okay, so the top sign, the top operation matches what you had originally, the a plus b or the a minus b, and then the sign in the bottom is the opposite of that. So if the top's positive, the bottom's negative. If the top's negative, the bottom's positive. And it's always a 1 sitting out front. So these are the 6 sum and difference identities. And again, you don't have to have them memorized, but you do need to be familiar enough with them so that when you see them, you'll know to use them. And you can use them either direction. Usually we're going to be trying to rewrite something on the left side and convert it to the right side, but it's just as possible to be given something on the right side and having to convert it to the left side. Okay, and we'll kind of look at some of both sides of that. So before we get into, there's a few other identities we get into, but I want to revisit that mistake that we talked about just a minute ago, where we tried to take sine of a plus b and rewrite it as the sine of a plus the sine of b. And I want us to evaluate the example using the identity. Now again, we know, we already talked about this, we know that the sine of 90 degrees is 1. So that's just, we can actually compute that because we can add the 30 and 60 degrees to get 90, and we can compute that using the unit circle. So how would we do sine of 30 plus 60 without combining them into 90? How would we compute that using the identity? Okay, so we know from our identities that the sine of a plus b is equal to, remember, we're going to have a, b, and we're going to have sine, cosine, cosine, sine, and for the sine, whatever our plus or minus is here, it's going to be the same here. So the sine of a plus b is the sine of a cosine b plus the cosine a sine b. So to apply that in this example, so we have the sine of 30 degrees plus 60 degrees. That is going to equal the sine of 30 degrees, because the 30 degrees is the a, and b is 60 degrees. So sine of 30 degrees and then the cosine of 60 degrees plus the cosine of angle A, which angle A is that 30 degrees, and then the sine of B, and B is 60 degrees. So we've rewritten the sine of 30 plus 60 as 4 trig expressions. So we need to go through and evaluate all 4 of these. So from the unit circle, we know the sine of 30 degrees is a half, and we know the cosine of 60 degrees is a half, plus we know the cosine of 30 degrees is a root 3 over 2, and we know the sine of 60 degrees is also root 3 over 2. So if we simplify this expression, what do we get? A half times a half. So you just multiply straight across. So 1 times 1 is a 1, and 2 times 2 is a fourth. So a half times a half is 1/4. We multiply the second pair of fractions. So a square root of 3 times another square root of 3 technically is a square root of 9, which turns out to just be 3. And then we have a 2 and a 2 on the bottom, so that is a 4. And if you look at this, hopefully we see what's going to happen. 1/4 plus 3/4 turns out to be 4/4, and that is in fact equal to 1, which is, again, that was what we were hoping it was going to equal to, knowing that the sine of 90 degrees is 1. So here's just, again, a quick example. If you had the sine of 30 degrees plus 60 degrees, again, obviously you can do this as the sine of 90 degrees, but in most cases you can't add these together. And so you need to be able to split it apart using our identity. Once you split it apart, the whole goal in this is that the a and the b are numbers that you know what the sine of a is. It's like 30 degrees, and you know what the cosine of b is, so 60 degrees. So usually the a and the b should be numbers on the unit circle. So pi's over 3, pi's over 4, pi's over 6, 30, 45, 60 degrees, right? And then we can compute that, and we can get these exact values, okay? And they should match up. All right, there's a few more identities we need to throw into the mix here. The 2 groups we're going to look at here, these co-function identities, these are not on the identity sheet. So this is something that if you wanted to use them directly, you would need to memorize them, but you really don't need to, because you can just use the sum and difference identities. I'll kind of show you how to do that here in a minute. But supplementary angles, remember, goodness, from geometry, from trigonometry, supplementary angles mean that they're 2 angles that add up to 180 degrees. And if we think about the unit circle, 180 degrees is the same thing as pi. So what this is saying is, if you had, say for sine, if you were to compute the sine of 2 complementary angles, so say you wanted to compute the sine of 60 degrees and compare it to the sine of 120 degrees. Okay, so 60 plus 120 is 180. So those 60 and 120 are supplementary angles. Well, what's the sine of 60 degrees? From the unit circle, we know that is a half. What's the sine of 120 degrees? Well, the unit circle also tells me that's a half. Remember, reference angle. So what the supplementary angles tell us, what these identities tell us, is for sine, if you compute the sine of two angles that are supplementary, you get the same value. For cosine and tangent, you get the opposite value. So if I did the same thing for cosine and tangent, if I did 60 and 120, for cosine, you'd get root 3 over 2 and then a negative root 3 over 2. So it just changes, the same number just changes sign. So similar thing for tangent. All right, so complementary angles is our other kind of subgrouping of the cofunction identities. Again, complementary is two angles that add up to 90 degrees. And so 90 degrees is pi over 2 radians. So that's why we have the pi over 2 floating around in there. And so this says that if you tried to compute the sine and the cosine, for example, of complementary angles, you get the same thing. Okay. So for an example, if I tried to, we could do, we already did the one, 30 degrees plus 60 degrees is 90 degrees, right? So if I tried to compute the sine of 30 degrees, and I wanted to compare that to the cosine of 60 degrees, well, the sine of 30 is a half, and the cosine of 60 is also a half, and lo and behold, those are equal to each other. And that's sort of what these first two statements are telling us. And it doesn't matter which direction. If you're doing the complementary of sine versus or the complementary of cosine, they're flipped relationships. Visually, what's happening here is, again, remember we defined our sine and cosine and tangent in terms of an acute right triangle. So say this was angle A, and angle B was the other acute angle. Well, we have the hypotenuse, and say we're talking about angle A. So from angle A, we have the hypotenuse, we have the opposite side, and we have the adjacent side. Okay. Well, if you're talking about angle A, if we did sine, the sine of angle A is the opposite over the hypotenuse, right? So that's opposite and hypotenuse. But if I were to compare and look at that from cosine of B, so if we start talking about this angle, then really the vertical side of our triangle is the adjacent side. But if I left it sort of the same name, it would still be the same thing. It would be the opposite over the hypotenuse. So because of this nature of the right triangle, these two angles or these two values are equal to each other, because it's just flipping the opposite versus the adjacent kind of relationship. So again, the A and the B angle have to be complementary, because they have to add up to 90 degrees, because the whole triangle has to add up to 180 degrees, and you already have a 90-degree angle. And so that's just kind of a quick visualization of why those complementary angles work the way that they do. All right, so let's look through some examples here. We'll start off with just simplifying expressions, and then we'll look at computing values, and then at the very end we'll look at proving a couple identities. So with this first one here, we have the tangent of the quantity pi over 2 minus theta times the sine of theta. So when we look at this, there's a couple options here. We might automatically see that minus in there and think some difference identity, and that would be totally fine. It will work. But it's also got a pi over 2. And so when I see this pi over 2, I'm going to start thinking that's one of our complementary. It's our complementary identity. Okay. And so we know for the complementary identity, the tangent of pi over 2 minus theta turns out to just be equal to the cotangent of theta. And you still have the sine of theta being multiplied by that. So the tangent of pi over 2 minus theta turns out to just be the cotangent of theta. And again, that's one of the complementary identities. And so we could further simplify this using the identities, some of the identities we learned last time. We know cotangent of theta. I kind of grouped it into those reciprocal identities, but cotangent is the same thing as cosine of theta over sine of theta. So we're left with a cosine of theta over sine of theta times another sine of theta. And if you want to make it a fraction also, just put it over a 1. Well, I have a sine in the top and a sine in the denominator, and those are both just going to divide out and cancel. And so all we're left with is the cosine of theta. So this tangent of pi over 2 minus theta times sine of theta turns out to just be equal to cosine of theta. So it's a nice, easy little simplification there. Well, what if it gets a little bit more complicated? So we have the tangent of pi over 18 plus the tangent of pi over 9, all divided by 1 minus the tangent of pi over 18 times the tangent of pi over 9. So again, using the strategies that we had before, when you see tangent, one of the first things we try is to convert everything into sines and cosines. So we could rewrite all these tangents as sines over cosine. But unfortunately, we don't know what the sine of pi over 18 is. Pi over 18 and pi over 9, those are not our nice unit circle values. So even if we did that, we'd still have to do something else. But as I said before, you don't have to have all the identities memorized if they're on the list, on the identity sheet, but you should be familiar with them, okay? And so this looks very much like the tangent of A plus the tangent of B all over 1 minus the tangent of A times the tangent of B. So again, notice I have AB, AB, I have tangent plus tangent over 1 minus tangent, tangent. And so the identity says that this is actually equal to the tangent of A plus B. Okay, the plus here matches the plus in the numerator. So I could rewrite this entire fraction as just the tangent of A plus the tangent of B. So A, in this case, again, A is going to be the pi over 18, and B is going to be the pi over 9. So I could rewrite this whole big fraction as the tangent of pi over 18 plus the tangent of pi, well, not tangent, so the tangent of pi over 18 plus pi over 9. So just one tangent of the sum of the pi over 18 and pi over 9. Now, none of that doesn't come out to obviously be something that we can compute real quick. So let's try and simplify these fractions. So to add two fractions, we're going to need a common denominator, which pi over 18 can stay the same. 18 is going to be our common denominator. So if I need an 18 for the pi over 9, that means I have to multiply the top and bottom by 2. So I'm going to have a 2 pi over 18. So I have a pi over 18 plus a 2 pi over 18. And that turns out to be the tangent. If you add those, 1 pi plus 2 pi is 3 pi over 18. Okay. The 3 and the 18 will reduce a little bit. 6 goes into 18 3 times. So we have the tangent of just pi over 6. Okay. Now, how do we do the tangent of pi over 6? Again, you can memorize that if you want. It's just a unit circle value. I tend to think of tangent as sine over cosine. So I like to break it apart and think of sine over cosine. So sine of pi over 6 over a cosine of pi over 6. And I know sine of pi over 6 is a half. And I know the cosine of pi over 6 is a root 3 over 2. And then the 2's are going to cancel out, and you're just left with a 1 over a root 3. Okay, and so that would be our answer. So 1 over root 3 is what you would get for this original fraction of tangent of pi over 18 plus tangent of pi over 9 all over 1 minus the tangent of pi over 18 times the tangent of pi over 9. All of it is 1 over root 3. And again, the reason why I always rewrite tangent in terms of sines and cosines is it's several things less that I have to memorize. Okay, I don't have to remember what tangent of pi over 6 is. All I have to know is what sine and cosine of pi over 6. So I have to memorize, you already have to know the sine of pi over 6, pi over 4, and pi over 3, and pi over 2. Same thing with cosine. So, but if you had to memorize all of that for tangent, you know, it increases the amount of things you memorize. So just remember that tangent is sine over cosine, and then do everything in terms of sine over cosine. All right, let's look at another example of kind of simplifying expressions and computing values. So say we had the expression cosine of 145 degrees times the cosine of 35 degrees minus the sine of 45 degrees times the sine of 35 degrees. So the first thing that we should, again, I don't know what 145 degrees is, and same with 35. Those are not unit circle numbers, so I can't just directly compute this exactly. So we need to think about an identity. So again, this is where you should be familiar enough. As you work through these, you need to become familiar enough with the identities so that you can just look at this and be like, that's a fundamental identity, that's a sum and difference identity, or whatever it is, that's a cofunction identity. So if we look at this, again, if we get rid of the numbers, this is cosine of A, cosine B, minus sine, and notice the numbers, 145 here and here, 35 here and here, so sine of A and sine of B. Now, again, just using the strategy I had earlier, if we have, notice that it's still AB, AB, and it's still cosine, cosine, sine, sine. So when it was cosine, cosine, sine, sine, my little technique was that meant that was a cosine. When the two are paired together, so two cosines and two sines, it was cosine. If they're mixed, so cosine, sine, or actually sine, cosine, and then cosine, sine, then it was a sine. But anyway, I know this one has to be a cosine. And cosine, the other thing I said was that it's opposite. So because this is a minus, I know it's going to be A plus B. Okay, so I can take this whole initial expression and rewrite it as the cosine of A, which is 145, and B, which is the 35. So we have the cosine of 145 plus 35. So now we just have one cosine expression, not a bunch of the cosines and sines. And we can easily combine those together. So the cosine, so 145 degrees plus 35 degrees is going to be 180 degrees. And so originally the 145 and the 35 were not things I knew on the unit circle. But now we've worked this all together, so we just have 180 degrees. And 180 degrees is on the unit circle. Okay, on our unit circle, 180 degrees puts us over on the negative x-axis. And the coordinate there is negative 1, 0. Cosine, remember, is the x-coordinate. So this turns out to be a negative 1. Okay. Now, had you tried computing the original problem, the cosine of 135, cosine of 35, sine of 145, sine of 35, if you would have typed that in on your calculator, it would have given you a negative 1 answer. Okay. It doesn't always happen to be 1 or negative 1 or something like that. But again, this was a nice example where it worked out to be something we could do using the unit circle. And again, that's usually the hope, the strategy, is to get it to something that we can do on the unit circle. All right, let's turn it around and do something that starts easy. So this uses kind of the left-hand side of these identities, and then we move it to the right side. So how can we compute the sine of 5 pi over 12 and get the exact answer? Well, obviously 5 or anything pi over 12, pi over 12 is not one of our normal unit circle angles, so we have to figure out something to do with that. Okay, And there's several ways that we could approach this, but our thought process here is we want to figure out a way to rewrite the sine of 5 pi over 12 as the sine of either the sum of two values, or we could rewrite it, if possible, as the difference of two values. So the trick here is figuring out how to go about doing that. So let's just do some simple algebra here, if you think fractions are simple. So how could you break apart 5 pi over 12 as a sum? Okay, so your first option is just to think of a 1 pi over 12 plus a 4 pi over 12. Okay. Okay, and so we can simplify the pi over 12. We really can't do anything with. That's just pi over 12. But the 4 pi over 12, 4 goes into 12 3 times, so I could rewrite that as pi over 3. And so again, our strategy here, we saw this in some of the earlier examples, is we need these two numbers, the a and the b. We need those to be values that we recognize on the unit circle. So pi over 3, that's a nice unit circle number. Pi over 12, not so much. Okay, we don't know what the sine or the cosine of pi over 12 is. So we can certainly rewrite 5 pi over 12 as pi over 12 plus 4 pi over 12, but it's not going to be helpful. So let's try something else. So we could also say that 5 pi over 12, so we started with a 1, let's try it with the 2. So we could say it's 2 pi over 12, and then, so what do you add to 2 to get 5? You add a 3, so 3 pi over 12. All right, so let's try and simplify these a little bit. 2 goes into 12 6 times, so that gives me pi over 6. And 3 pi over 12, 3 goes into 12 4 times, so that turns out to be a pi over 4. Well, look at both of these, pi over 6 and pi over 4. Both of those are nice unit circle numbers. So this would actually be a good option, okay? And we could do the same thing for subtraction. So what are two numbers we could subtract to get a 5? Well, you could subtract a 6 minus a 1, right? So if we need to get a 5, 5 is 6 minus 1, so 5 pi over 12 would equal 6 pi over 12 minus a 1 pi over 12. And if we reduce those again, the 6 pi over 12 is going to be pi over 2, because 6 goes into 12 twice. Minus, but you can't do anything with the pi over 12. Now, the pi over 2, we can do that on the unit circle, but we can't do pi over 12. So let's go to the next step. So what's another way we could subtract two numbers and get a 5? Well, 6 minus 1 didn't work. So let's just bump it up. Let's do 7 minus a 2. Well, 7 pi over 12 minus a 2 pi over 12. I'm not even going to simplify this, but I know 2 pi over 12 will give us a pi over 6, but 7 pi over 12 isn't going to work because you can't reduce a 7 and a 12. So that means we have to go up to the next step. So pi over 12, so we did 6, we did 7, so let's do 8. So 8 pi over 12 minus, so 8 minus what gives you 5? 8 minus 3. So we're going to have 8 pi over 12 minus a 3 pi over 12, which does give us a 5 pi over 12. The 8 and the 12 are going to reduce. You can pull a 4 out. So 4 goes into 8 2 times. So 2 pi over 3, because 4 goes into 12 3 times. Minus the 3 and the 12 reduce down to a 1 over 4, so pi over 4. So in this case, 2 pi over 3, since it's a pi over 3, that is a unit circle number, and pi over 4 is a unit circle number. So I could break this 5 pi over 12 either as the sum of 2 pi over 12 and 3 pi over 12, or as the difference of 8 pi over 12 minus 3 pi over 12. Okay, either one would work. You just use the appropriate sum or difference identity. And then you're going to have to simplify the pi's over 12 into pi's over 6 or 4 or 3's and 4. So let's go ahead and just go with the sum option here. Okay. So I can rewrite, let's go to our problem. We have the sine of 5 pi over 12. So I can rewrite the sine of 5 pi over 12 as the sine of 2 pi over 12 plus 3 pi over 12. And I know that that simplifies a little bit. We have the sine of pi over 6 plus pi over 4. Okay, so we've already done that work. Okay, that's what we did on the side here, is we've already figured those fractions out, and we know that it works. That we know that they add up to the 5 pi over 12. So how do we still have to go forward. How do we compute what this all actually is equal to? So we have the sine of a plus b, right? So that is the sum. So we're using the sine of a plus b. So we're using our sine sum identity. And so we know that the sine of a plus b is the sine of a times the cosine of b. Sine has the same, so since this is plus, it's going to be plus. And then we flip the order of the sine and cosine. So it's going to be the cosine of a and then the sine of b. So what's my a? My a is my pi over 6, and b is going to be the pi over 4. So I can rewrite the sine of pi over 6 plus pi over 4 as the sine of pi over 6 times the cosine of pi over 4 plus the cosine of pi over 6 times the sine of pi over 4. And these four expressions, these sine and cosine expressions, all use unit circle values. That's why we did the stuff on the right side over here. So we know they're unit circle, which means we can compute them using the unit circle. So what's the sine of pi over 6? Again, from the unit circle, that's a half. Again, you have to memorize these. We then have the cosine of pi over 4, which we know the cosine of pi over 4 is root 2 over 2, plus the cosine of pi over 6, which cosine of pi over 6 is a root 3 over 2, and then the sine of pi over 4 is another root 2 over 2. So again, you have to have these unit circle values memorized, okay? All right, so the last thing is we really just need to simplify this stuff as far as we can anyway. So we're multiplying two fractions. We have a 1 times the square root of 2, which is just going to be a square root of 2 in the numerator, and in the denominator we have a 2 times 2, which is a 4. So we have root 2 over 4 plus, if we take in the numerator, a square root of 3 times a square root of 2. When you multiply roots, you multiply what's inside. So 3 times 2 is the square root of 6. And in the denominator, we have a 2 times 2, which is a 4. Okay? So we have a square root of 2 over 4 plus a square root of 6 over 4, which there's really not a whole lot you can do with this. You could leave it just like that. You could also, just since they already got a common denominator, you could write it as square root of 2 plus square root of 6 all over 4. So either of these two would be the correct answer. I'll just kind of circle out this bottom one here. But again, that's the exact answer. It's not as nice and as easy and as pretty maybe as, well, it's beautiful actually, but it's not as nice and easy as the sine of 5 pi over 6. But we still can come up with an exact value. If you wanted to check that, type in the sine of 5 pi over 12 on your calculator, and then type in this fraction on your calculator and make sure that they match. Make sure they're the same decimal number. All right, let's look at something that's a little bit more general in nature. So we're not computing the exact value. We don't actually know what a and b are. We're trying to compute the sine of a plus b. So that's again our sum identity. We're trying to compute the sine of a plus b, but we don't know a and b. All I know is that the sine of a is 5/13 and that the sine of b is a negative 3/4. We also know that a is between 0 and pi over 2. So an angle that's between 0 and 90 degrees means it's in the first quadrant. And we know b is between a negative pi over 2 and 0. So it's going to be a negative angle. And between negative 90 degrees and positive 90 degrees means b is going to be in quadrant 4. When we do when we do the quadrants, we write them with Roman numerals. Ignore all this line over here. That's just a glitch. All right, so we have angle A is in the first quadrant, angle B is in the fourth quadrant. We know sine of A is 5/13, and we know tangent of B is negative 3/4. And we're trying to use all of that to figure out what is the sine of A plus B. So let's get started on that, and then we'll see what we have to figure out sort of on the side. So we know the sine of A plus B. That's our sum identity. We know that's going to be equal to the sine of A times the cosine of B plus the cosine of A times the sine of B. Okay, so that's what our identity tells us. So in order to compute this, we need to know sine of A, cosine B, cosine A, sine B, which we actually already know sine of A. Okay. So sine of A we already know is 5/13. But I need to figure out what is the cosine of B. And also what's the cosine of A and the sine of B. So I don't know any of those three. And so we're going to use all the other given information to figure those three out. So let's start off with A. So we know the sine of A is 5/13 and we know A is in the first quadrant. So let's draw something that would represent angle A. So if we draw our axes, angle A has to be in the first quadrant, somewhere in the first quadrant. So here's angle A. And when you draw that, go ahead and draw a triangle. So let's draw a vertical line down from the top of your angle down to the x-axis. And that's going to form a right angle with the x-axis. Because we're talking about the sine of A, we know sine of A is 5/13. So I could think of, with sine, I could think of that as being the opposite side, which is the vertical side of the triangle, as 5, and the hypotenuse as 13. So I know the sine of A is 5/13, and that's opposite over hypotenuse. Okay. So what else do we need to know about angle A? We also need to know the cosine of angle A. And so we need to figure out what's the adjacent side. Okay. In order to figure out cosine, we need the adjacent side. So let's just call that x. So we know the cosine of angle A is going to be x over 13, but we actually want to compute x. And that's just going to be the Pythagorean theorem. So x squared plus 5 squared has to equal 13 squared. So x squared plus 25 has to equal 169. And then if we subtract the 25 from both sides, we have x squared is equal to 144, which means the adjacent side x is 12. Okay, so we know this is 12 here. So cosine of angle A is going to be 12/13. And so that gives me 2 of the 4 values that we need to complete this. And so we want to do a similar thing with angle B. So let's draw our axes. Now we said angle B has to be in the fourth quadrant because it's from 0 down to a negative pi over 2. So let's draw an angle in the fourth quadrant, and we know angle B. So that's a clockwise rotation, right? It rotates from the x-axis down into the fourth quadrant. And just like we did here, let's draw a vertical line from our bottom angle up to the x-axis, and it's a 90 degree. And we're told that tangent of B is a negative 3/4. So remember, tangent is the opposite, which we're going to say is 3, over the adjacent, which is 4. Now, what do we do with this negative? Okay, I think we looked at examples like this before, but remember when we talk about the dimensions of your unit circle, which we're not doing the unit circle here, but cosine was the x, sine was the y. So if we think of this 3 as sort of a y coordinate, since it's below the x-axis, this 3 would be negative. Okay, the 4 points to the right, moves it to the right 4 units, and then we're going 3 units down. So that's where this point is down here. So we have 4 units to the right, 3 units down, so there's the negative 3. In order, we need to know cosine of b and sine of b, which means for both of those we need to know the hypotenuse. So we'll just call that h. So we're going to have, again, this Pythagorean theorem, so negative 3 squared plus a 4 squared has to equal h squared. Negative 3 squared is 9, so 9 plus 16 has to equal h squared. 9 and 16 gives you 25, so that's equals to h squared, which means h is 5. Now the hypotenuse is always going to be positive, it's just a length. So we know the horizontal side of the triangle is 4, the vertical is a negative 3, and then the hypotenuse is 5. So what is the cosine of angle B? So for B, cosine is the adjacent over the hypotenuse. So that would be 4/5. And sine of B would be a opposite over adjacent, so a negative 3/5. So we're almost done here. We figured out all 4 values for the sine and cosines of A and B. It's just a matter of simplifying stuff now. So multiply fractions. 5 times 4 is 20. 13 and 5 is 65. Plus, we're going to have one negative, so it's going to be actually plus a negative, or you could say that's a minus. 12 and 3 is 36. 13 and 5 is 65 again. And so if we combine our fractions, and nicely here we have common denominators, so 20 plus a negative 36 would be a negative 16 over 65. Okay, and so even though we never actually found out what angles A and B actually are, we just knew what their ratios were, and so from the ratios we can do Pythagorean theorem and find the missing sides of the triangles, and that allows us to figure out all of our trig values. Okay. All right, for the last 2 things we want to look at here is just how do we use our identities to to verify other identities. So the first example here, we have the cosine of the quantity pi over 2 minus theta, and we want to show that that's actually just equal to sine of theta, which you might get real excited because you look at that and you realize that that's the cofunction, one of the cofunction identities. That's one of our complementary identities. And so you'll just be like, yes, that's true, and we're done. Okay, we'll just make that substitution. We'll say that cosine of pi over 2 minus theta is equal to sine of theta, and so it's done and done. Okay, but we can't. Okay, we're actually trying to prove the complementary identity, so you can't use the complementary identity to prove itself. So we actually need to use an identity. So let's look at the left side. We have the cosine of the difference of 2 values. So this is really the cosine of A minus B on the left side. So the cosine of A minus B, which turns out to be kind of a longer expression. We know for cosine it's going to be the cosine of A times the cosine of B. And it flips signs, so since this is a minus, we're going to get a plus, and it then becomes the sine of A times the sine of B. Okay, so I'm going to use this identity. That's the difference identity for cosine, and we're going to plug in our pi over 2 and our theta. So that means we have the cosine of pi over 2 times the cosine of theta plus the sine of pi over 2 times the sine of theta. Okay, so what is the cosine of pi over 2? Well, again, going back to our unit circle, pi over 2 is the positive y-axis, and the coordinate there is 0, 1. So what is the cosine is the x-coordinate, which is a 0. Sine, we're just stuck then with the cosine of theta, plus the sine of pi over 2, which is the y-coordinate, that's a 1. So we have a 1 times a sine of theta. So 0, this is just all gone, that's just a 0, and 1 times sine of theta is in fact sine of theta. So we're able to show, so we actually just proved one of the complementary identities. Okay, and you could prove all the other ones in a very similar process, but so we can't use the cofunction or the complementary identity to prove itself. We actually have to use a different identity, which in this case we just use the difference identity, which is one of the reasons why I said earlier that you don't need to really memorize the complementary or supplementary identities. You can always just use the sum and difference identities. It just might mean an extra step or two of work, but anyway, we have proved the first one of the complementary identities, and the others again would follow in a similar fashion. So let's look at something that's not so clearly one of those identities. So our last example is we have the tangent of the quantity x minus pi over 4, and that is, we want to show that that is equal to the fraction of the tangent of x minus 1 divided by the tangent of x plus 1. Okay, and again, remember when you're trying to show an identity, I should have mentioned this on the last example, but when you're trying to prove an identity is true, you can't assume it's true, which means you don't work both sides of the equations like it is an equation. Okay, you have to work independently, either the left side or the right side, or you can kind of play them both, but your goal is to get them to match up. Okay, and again, I'm going to start. Let's start just on the left side here. So we see the tangent of x minus pi over 4, which when I see that, again, my immediate thought is this looks like the tangent of the quantity a minus b. And we know that the tangent of a minus b, that's one of the difference identities. It turns out to be the tangent of a minus the tangent of b all over 1 plus the tangent of a times the tangent of b. So remember, it's AB, AB. Since it's a minus here, it's a minus in the numerator and a plus in the denominator, and then this over here is a multiplication. So let's plug everything in here. A is the first term, that's the x. B is the second term, that's the pi over 4. So that gives us the tangent of x minus the tangent of pi over 4, and all of that is divided by 1 plus the tangent of x times the tangent of pi over 4. Alright, so this should sort of look closer to what we need, right? We have the tangent of x minus something, which over here we hopefully get tangent of x minus 1. And in the denominator, we do have a 1 plus a tangent, but we have this pi over 4 thing. So what does all this turn out to be? So we have the tangent of x minus, so what is the tangent of pi over 4? Remember, tangent of pi over 4 on the unit circle, pi over 4 is 45 degrees, and that's the coordinate there is root 2 over 2, root 2 over 2. And when you do tangent, you're doing y over x. So the tangent of 45 degrees is, thankfully, a 1. So in the numerator, we do get the tangent of x minus 1. And in the denominator, what do we get? We have 1 plus, well, we still have that tangent of x times, well, what did we say the tangent of pi over 4 was? Well, it turned out to be a 1. And the tangent of x times the 1 is just the tangent of x. And so we could rewrite the order of that. So we have tangent of x minus 1 on the top, and I can rewrite and simplify the denominator as tangent of x plus 1. And that, again, that turns out to be what we were trying to prove to begin with. Okay, so there we have, again, we verified this original identity using the sum identity for tangent.